Just raise your hand or throw it at me. We have a small company here, which is nice, and it's okay to ask and answer a question to change the flow of the story. So it's not exactly a talk about performance, but it's a talk about making your Java options not default, and which will give you performance and other nice effects. And just think about what are you deploying to your production, which is probably critical to you, or if you have some customers, to your customers. So I primarily work on OpenJDK as a developer, but I also travel a lot, like 2 months a year, which is pretty much getting that to different conferences. And I worked at a company named Bellsoft, and we participate in different open source projects. Well, the two, I would say, the most important ones, OpenJDK and Linux. And we release, and also GraalVM, of course, which is kind of near to OpenJDK. Now it's a part of OpenJDK. And we release our own binary distributions on top of the projects. We're quite competent in that. The JDK distribution is called Liberica JDK. Probably you've heard about it. If not, we'll see some details later. It's an OpenJDK distribution, so if you need an OpenJDK, just get it. We also release our GraalVM binaries. The name is Liberica Native Image Kit, and a special thing that allows to run either of them in a most optimal way, and we'll probably see some demos again. It's called Alpakita Linux, which is a tiny Linux, Alpine-like, but it has its own things and features. And it has support as well as other products. And we're quite visible, especially in OpenJDK space, where we just contribute a lot to upstream and to update projects, because we support one of LTS distributions that has LTS releases with S meaning support. So I start with this talk with one of my favorite stories about a big American company where our friend works. And some time ago, they decided to perform digital transformation. I really like this words, just digital transformation. And they decided to modernize their IT infrastructure, their Java projects. So they have a lot of things written in Java, many customers and users. They sell a lot of different products, multiple lines of businesses, and so they decided, okay, let's make it modern. We have budget for that, and it was somewhere around COVID. So they had that budget. I believe now they don't have it. But anyway, so they hired some developers, assembled teams, developed some architecture, right? All that microservices, all that new messaging systems, all that new container stuff. So they've moved to cloud from their own data centers. They chose the cloud provider, and of course, they started with some presentation. How much will they save on moving to the cloud, right? So they performed all that changes. Of course, there were some delays, but anyway, it all has been developed, tested, and deployed. So many people started getting their bonuses, right? Because it was a successful project, maybe with some small delay. And all of them were happy, just like operations started to support all that running. Developers fixed some bugs, testers tested it, and then cloud operations tried to shape it only in a big cloud. Everyone's doing their job successfully. Unless their management, their upper management, finally started getting bills for their cloud deployments, right? Because developers don't pay for the cloud. Cloud operations don't pay for the cloud. DevOps don't pay for the cloud. Like their financial department, their major business, they are paying for the cloud. And they see all the bills just after it all happened. So they have no plan B, no way back. We have to do something. What was wrong here? Okay, so everything was right. So it was, well, maybe not perfectly, but somehow properly developed, properly deployed, properly supported, but just the improper number in the end. Well, yeah, I hope our today's build won't be as much as this. So business had its requirements, but probably that were mostly requirements for finally making this done, making this completed, and making the business functioning in the new circumstances. And the cloud operations, again, had their requirements just to make it runnable, to keep it on, right? Just to avoid downtimes. And developers, they had their own tasks. Like we need to develop this and that microservice to move this functionality to update Java versions. So they didn't have the goal of having it optimal. The tiny detail, just think about the cloud cost. And that also implies taking many other actions. Analyzing your containers, analyzing your performance. Basically, two parts of today's topic. So they've put Java into containers. And we know that for quite some time, for several years, Java is very container aware. And if you use recent versions of all LTS releases, you're good. It really works fine. You just have to tune it a little, or you just have to think of what are you deploying and what are your versions, what can you do with them, how can you improve your performance or your cloud costs within such limitations of the versions that you may use. So, of course, the important information is that what hardware resources we pay for, how much we underutilize, how that can be used, how it can give some profits. Maybe you can earn more just to cover all your costs. Maybe you don't need to lower them. That may be the case. So that's a classical SRE picture. So besides of reliability, besides of stability, you have some other objectives. And you just have to write them down and track them and try to accomplish all the goals that you set. So in that objectives, we start with something that's visible to end users or to end systems that consume or input data to your big system. Like, if I click a button on a website, I want it to be responsible, right? I want to get some result, that things change, and to get the new information quickly in a certain time frame. Which means some service must respond, some network quality must be provided, some database setting must be made. All that serve to fulfill some service level objectives, saying that we must observe some indicators, something that we can measure technically inside our software environment and compare with the target values. So for every part of the system we can see as a separate one, we should define those SLAs, SLOs, and choose the indicators for that SLOs to track them. And among those indicators, there are probably most important ones, or the ones that I'll have more, the ones related to JVM. All that we can observe from the JVM, all the information we can get from a running application. Well, and we can even play cards with that information, saying, okay, we have those indicators like the response time or the GC post time, some percentile, for example, like 95th percentile. We want it to be less than, 90 milliseconds. And today it's 50, which means probably we are better than, today it's like 100. We're better than 150, but we are still worse than 90. And that's measurable. We can track progress. We can see how it influences business, how it influences costs. So it all can be written and those cards can be played. Well, some other things we can look at. Obviously, uptime, and other stability metrics. All the GC metrics. You can see quality of service in general, whatever it means. We can invent some indicators and track them as showing that technically our customers should be satisfied. Doesn't mean that they're really satisfied. It can be measured from the outside. And of course, times like how our services start and get ready to respond to their workloads, like time to performance, time to getting up, and latency, as I already mentioned. When the application is warmed up, it reaches some peak performance, right, until it's crashed or whatever happens. And it also can be measured, and this is probably one of the easiest things to measure. And it also can be used for scaling, as well as that CPU consumption, which is also popular. And we can look at different things, like the quality of memory utilization, whatever, and different tiny internals like save point, like time to save point, and other information that reflects latency, if you talk about JVM specifics. So we can invent many things. And we try to finally settle that, to fulfill the objectives, saying we really push our system to have a good latency, to finally reach that golden 95th percentile values. And on the other hand, we try to lower costs, right? Because sometimes we increase performance with some extra costs. We can use a more expensive hardware. We can throw in more engineering time, whatever it takes. So we have two goals, and they somehow balance. And well, unfortunately, sometimes they don't balance, because if we want to try to reach both, we can do both, but in a reverse way. We just can fail both. So we can have a very bad cost model, very high costs, and at the same time, poor performance and still broken SLAs. If we do nothing, that's what likely will happen. So why it doesn't happen? We threw in some resources, but they won't be used automatically. We will have that underutilization problem. And in many cases, it's related to some defaults, some convenient defaults that we use. Like, let's don't try to invent autoscaling ourselves and to properly set it up. Let's just use some automated one that's provided by the cloud provider. Says, hey, we also offer you free autoscaler. You can use it easily in our free, or not so free, managed Kubernetes, which you can't afterwards move from. But it's convenient, right? It's easy to start, and it really gives you a boost, and it saves your time in your development time, which you might not have. You just start using it. And surprisingly, it correlates with cloud costs that you get in the end. If you have some average team, and we all have average teams, right? If you don't think about every detail, which you probably should not, you will fall into that statistics. So like, if you rely more on some out-of-the-box solutions, you will probably spend more under the cover. That's it. Yes, and it's the same cloud provider that offers us free autoscaling sends us such boxes. And you see in that boxes, yes, we feel that something is wrong, but the target was accomplished. We have that product delivered to our house. it's safe, it's not broken, it's not damaged. So our service works. It just requires slightly bigger resource to be delivered and, some waste afterwards. But of course, it could be made better, which means we must have such an objective. We must say, hey, let's utilize that spare space and have a more dense deployment. And we underutilize all kinds of resources. All that you can imagine, network bandwidth, right? I/O for some disks, local or cloud-based, your CPU, your memory. It all can be underutilized. And we pay for all that resources. So all that is built either on-prem or in cloud. It doesn't matter. It just costs some penny. So as I mentioned today, you have a monument to a container, which is a basement of deployments nowadays. It's really convenient. I was amazed when I first saw it, because we have seen some Linux isolation, some pre-container technologies, right, in other operating systems for years. But as soon as this became so convenient, so simple to use, it turned to be a killer feature, and it just turned out all the industry. So we definitely use them. It's a standard shipping unit. So maybe the format will change, but the concept will stay for long, that's for sure. That's the cornerstone of today's deployments. And then we put a JVM inside that container. We take our application, we take a JVM. What do we put, by the way, if we use native image? We also put a JVM there. We just have that JVM inside the native image, and we have our application code, and we still deploy all that together in the container. So the classical JVM tries to utilize some container resources, but it's still it's very conservative. And we have just discussed it yesterday, by the way, like in some smaller open JDK circle. So there are proposals. Let's raise the bar. How do we utilize that resources? How we follow the actual CPU given to us? What does it mean? Because even if we kind of try to use a fraction of a CPU, it's sometimes different how scheduler works. So it's not a trivial task. Even in the case of memory usage, which is by default at 25% of your container's memory. At some early stage, it was just 25% of your machine's memory. Now that's not an issue. But 25% of your container memory for your Java heap, isn't that too low? What do you think? What do you typically put? Like who puts 50 and above? 75, yes, that's our favorite number, 75. Who puts nothing? Right, so you get that 25. So you don't use 3/4 of your container memory, and you still pay for it. And there are also JVM ergonomics, JVM heuristics that change depending on the actual resources that JVM sees in the container, but they don't change on the fly. They are detected on startup, and that's it. So some clouds offered a trick, saying, hey, we know that you need as many resources just to start and warm up your application. And they are mostly consumed at the very beginning of the lifetime, like first 1 minute, 30 minutes, 1 hour of the application's lifetime, just to let just-in-time compilers work and compile your effective code and be finally fast and responsive. You can get a CPU boost on that time. And that really works as soon as you have spare resources on your node. But if you don't have spare resources on your node, if you just take 16-core node and split it by 4 pods, right, and they all have 4 cores, where will it get additional CPU resources on startup? It has no such place. It just has All their CPUs will be occupied by that. Of course, if only one part is restarting, if one pod is restarting and other pods don't use that CPU, probably that will help, but it depends. So the JVM also survives if we're too greedy. So many people still give JVM containers less than 1 core. I really don't know how JVM should work in this way. But it still works, though especially if you give it also low memory settings, it will switch to serial garbage collector, for example, which is sometimes surprising. But you must remember that it's not really an issue by itself. It's just a different heuristic, a different garbage collector that probably gives you a lower footprint, especially if you don't put some load on your application, and likely a better performance, because you don't have resources to run actually concurrent garbage collector with many parallel threads. You'll still have like 1 core or less, or slightly more, but less than 2. So we need also to see how much other resources do we consume to properly limit all that heuristics to tune the JVM. And that requires not just things related to our Java part of the application, but also some native parts. Like the JVM needs resources itself, and we may use some native resources, native memory, for example, or we can call libraries or whatever. So we might require something else running besides of our Java code, and some memory occupied besides of our Java heap. So how do we detect that? At least for buffers and something that we use from inside of the JVM. We'll use native memory tracking. We'll use profiling, right? And see what consumes CPU and memory, what consumes allocation, where are our native allocations. Okay, so we prepare that containers and throw them into a container management system. So it can be a proactive one, like Docker, right? And we say, hey, just do this thing with that container image or that specific container. Or it can be just declarative, like Kubernetes, which is great. You just say, I want the final result. I don't care about the actions. Just do it for me. And it really starts some containers somewhere within the resources that you provided. So we take our JVMs, we take our containers, container images with JVMs, and run them as containers on some ports in Kubernetes. And we regulate that deployment, or maybe it depends on who we are. Like we as developers or we as operations, right? We do it differently. As developers, we don't do it. So we say, we won't tune any settings because operations will do it for us. And what operations do? They just take some containers and run it. Nobody tunes it. They just say, hey, we have budget for that resources. And they set they definitely set some requests and limits, but they don't care about the JVM. And that leads to some bad results because we fall into the default settings, which means that the JVMs may crash, which means that the resources may be underutilized. So we have to care about both. So that's a real DevOps, because we must see what's inside the container. We must prepare that to be ready for some high loads, and we must test that loads. We must understand what are the resources that we require to run normally, and what's our strategy to go beyond that. Because that company that I mentioned, okay, they somehow managed to operate, like probably they started to do it in the beginning of the year. And in the autumn, they had Black Friday, which means they are all the amount of requests, it just doubled or tripled. And they started to survive, try to survive all that increased loads. Of course, well, after the first Black Friday, they got a lot of experience, so at least their operations were ready to keep it running. Again, with the price of a high cloud costs, right? You just say, hey, we need some more resources, and what do? You do horizontal scaling. Okay, we just say we have a doubled number of pods. Well, it also takes some time to start them, and probably we will survive the increased load. But you might not have that additional amount of pods because everyone is having Black Friday and Black Friday. Like cloud providers say, hey, if you use pod instances, they are the instances that may be unavailable for you because they're cheaper and, well, the first come, first served. That's it. So for such increased workloads, for such occasions, you must clearly understand what are the critical services for your operations, for like business days. What are less critical services that may be, that their SLAs may be sacrificed to let the more critical services run efficiently and to scale. And for the critical services, of course, you must guarantee that they will have that necessary resources, right? And resources necessary for JVM to get the right performance. And you must measure what resources do you need and what performance will you get so you could plan, right? That not only concerns the JVM, of course, all your components must be tested, like the database, etc. We'll just talk about it a bit later. So as I said, it may be costly, right? But it can be controlled. Scaling, horizontal scaling. Unfortunately, vertical scaling is not really possible right now. So even if you can enable experimental Kubernetes features, Java won't react to it. It just stay as it is. And if you do kind of normal pod resizing, you will just get a pod restart. So your JVM will have to warm up again to collect all the data in caches, and it will just take a lot of time. By the way, it could be done almost instantly in some cases. If you know what information you should have on startup, and it doesn't depend on some external sources like network, etc., you can actually save all that. You can use the checkpoint and restore functionality and have an instant startup for your services. That's not the topic of this talk, but it really can be solved. But whatever. When you plan your scaling, you also plan your cost model, right? So how much will it cost you to respond to a certain load? And what are the key indicators that you use for scaling? If it's CPU, probably it's not the best, right? If it's the incoming traffic or incoming number of requests, that's probably better. And you still will use CPU and memory consumption as an indicator of your health, right? But what are the golden practices of operations? Like if they look at CPU consumption, what's the typical health cutoff point? 100. No, it's not typical. 100 is not typical. I would say like 80 is typical, which means what for is the other 20% is used? Wasted. So just scale. If like just leave a small gap to be filled and give you time to scale. That's why you need that cap. You don't need that to still survive the increased load. You will survive it with a new instance, but you need time to provision that instance. And that's why you need the cap. It's the same as for memory, and you have to test it. Otherwise, it's 80%. Still not bad. Yeah, and if we have some systems we depend on, they limit our scaling. It's obviously like Amdahl's law, right? Which is if our database responds only 100 requests per second and we have one service or more services dependent on that, they altogether won't give you more than 100 if any request requires a database round trip, obviously. So you have to scale your root system first, right, in database in that case. Or it may be Kafka or some other microservice, right? It might not have enough replicas, for example, or some information might be not cached. Just analyze it. That's one of the slides that I change every year, right? And it's still true. So it started. It has its ancestors in other presentations as well. So it is true for many years. So services just continue being broken from time to time. What can we do? We can try to minimize that occasions, and we can also react and just fix things. The Kubernetes helps us if something is crashed or killed, you'll have a new instance. Right, and we will look at some microservice example. I have to show some bits. In the presentation, the data is collected for Spring Boot Pet Clinic example. It's a famous Spring Boot sample application with not the most recent version, but still the actual one. It's 3.x, 3.2 in this case. The good thing about Spring 3.x is that it can be easily converted into a container image. It can easily be built as a native image, and it can easily be built as a container with a native image. And if you know the concept of fat jars and thin jars can be used to optimize your container deployment, but it's easier to understand what's the amount of disk space and other memory that we need if you look at the fat jar size. So this application in that version just derives the almost 60 megabyte fat jar, and if you compile it to native image, it will be almost like 190 megabytes. So native images are smaller or bigger than jars, but we also need JVM to run the jar, so we need JRE, which adds some, but not that much. So in case of JRE, it will be less like than 100 megabytes. So combined, it will be less than the native image. Especially funny part is that your native image doesn't contain any debug information by default. And if you build it with debug support, it will become slightly 2 times larger than the original. Now, well, that's a separate topic. I have a talk on that, so invite me again. All right. We can package either of our finally compiled application formats. It's a jar file, it's a set of class files, jar files, or it's a native image, whatever. We need a container image. We want to run a container, so we need to produce container image somehow. So who doesn't use Docker files here? And who uses them? Yes, everybody just writes a Docker file, which is not right and not wrong. It's okay. In most cases, it's right. Just do it carefully, and you'll get a perfect result. Care about what's in the Docker file. Follow the optimization best practices for Docker files, and you'll get good results. And you can also use tools. You can use build packs. You can use a Google zip that drives the files. Like you can even create containers without Docker installed, which is sometimes useful, especially in CI. Well, all those things work, but you still have to care about the magic inside. And people might think that there are magical tools, like which will take your application and turn into a container which will work perfectly. I know only one such tool, and it's not perfect itself. Those are build packs. But cloud providers again say, hey, we offer you magic tools. They don't say it explicitly, but they make you think so. But those are actually tools just to bring your application to their cloud. And those tools really help you a lot with that. They solve all the boilerplate with JSON and YAML files, all the tokens, all the silly settings that we still have to write by hand, or we have to use their tools. Right? So they sometimes even require you to have a Docker file. And they try to replicate your original environment if you make that digital transformation. And finally, they do nothing. They do the major part related to your performance, to your Java options. So even with a Docker file, which the example here might be a bit outdated. I heard that some things it's not necessary anymore, like security, EGD, different random is not necessary anymore for Spring Boot, so forget about it. All the rest is actual, I think. So you can use some base image. Just who uses OpenJDK as their base image? No, please don't. Because if it's just called OpenJDK, it's a deprecated image. It's written on its main page. Just don't use this image. It's deprecated. It's just for the reference. It's that you can write it and it will work, but it doesn't mean that it's right. So here we can just take Liberica runtime container. And we can say JDK Slim, etc. And we just create a user, put the fat jar in this case, but we also can place a thin jar there. We have some tutorials on that and whatever. So you can do it manually in your Docker file. You can use appcds and crack in your Docker file. It's possible. It's not that complicated. You can put native images in Docker file. You can put Java options there, right? Just don't forget about properly sizing your memory. And here, in this case, we already assume the amount of memory we will have in our pod. Because we say, okay, with the pods we are going to have, 80% is fine. The rest, 20%, will be sufficient for our JVM to run, for all our native dirty things to run. It's okay. And we just start our application. That's just one variant. It's not a canonical one. There is no canonical one, except if you use Ubuntu, it's canonical. Okay. So you can forget about Docker files, right? You can say, hey, please create a container from an application from just a regular Java hello world. And you have a tool for that. That's called a Packeta build pack for Java. And it's based on Liberica JDK, by the way. So the default Java build pack uses Liberica and provides you a container. And even if you use a more complicated stuff, like you use a framework, you can use Quarkus, you can use Spring Boot, and they have their own build packs stacked and built on top of that Java build pack to handle all the machinery for your Spring Boot, for example, to create a proper container which won't break if you start it, and which will try to utilize your machine's resources, which is great, I think. Well, 17, not true anymore, I think. It's 21, I just checked it today, but we can regulate how it all works. It all can be regulated in Spring Boot, and there are some defaults that can be overridden. And we can just issue a simple command, which you won't see because you sit too far away from the screen. But I will read it. It's just you launch Maven, and you say Java version is not necessary. The profile is optional. In this case, it's profile native. And we say Spring Boot build image for us. That's it. You get an image in your local registry. So many things will be solved for you. We'll use very advanced under the hood magic, real magic, where all the build process and all the Java build process, all the native image build process, all the container build process will happen in containers. So it will be an environment that doesn't depend on your host machine, unless it must be runnable there in containers, which is very convenient, and it's very suitable for CI. You don't need things. You just have to provide a Java to run Maven, right? And you have to have the container registry and your source code. And in the end, you get the image in your container registry. And then you start such a container. Your application is not started right away from the very beginning. First of all, a little starter is executed, and it calculates the necessary memory settings, looking at the environment, and says, hey, I know what are the options for the Spring Boot. I can assume how much native memory do we need. All the rest memory can be used for the Java heap. And it works really well. So you don't specify your XMX, but you get it properly calculated. And you also get some other useful options for free that allow you to diagnose your application when it exits and then it runs. And it can be dynamically tuned by different options. So yeah, this machinery requires some other languages besides of Java. It's funny, but we have our own stack, and we really wonder how it works. Really like to poke with Go and Ruby and whatever. So there are certain settings, as I mentioned. I won't dive into much details, but you can derive different images here. Like the default image, which is not here, I think. If you use just from OpenJDK image, it will be just terribly large, and it will be like half of a gigabyte, and it's not a supported image, but though you still can run it. But you can get a small image as 100 megabytes just for free, just by manually writing a small Docker file. Or you can use build packs and still get a slimmer one, and don't have to write any Docker file at all. So we can optimize our containers, we can optimize our applications, and we can be prepared for the Kubernetes deployments. And it depends how we size the containers. I already mentioned that the sizing must take into account how JVM works. And we can see it in action. Like take this microservice and perform dummy performance tests, because the database is not shared and it's in memory, and only one endpoint will be poked. But anyway, it's a performance test. And we can compare different results, and we can compare different configurations. So we can select which ports will we use to size our application. We can use 2 ports and smaller JVMs, or we can use larger ports and 1 JVM. Or we can use lots of ports and that half of a core deployment. Just pretending it gives us some scaling, gives us some good results. Well, we'll see. But anyway, we should start with this sanity checks, trying to scale the application vertically, looking at its actual behavior without any containers. And here we can start compare things like different JVMs or different JVMs and native images, right? Here we get some golden number, right? Like 5.5 thousand, 100,000 requests per second. A lot for such an application. Typically, it's like an order or 2 of orders of magnitude lower for typical Spring Boot services. But anyway, we also have some warm-up curve. And we must understand that warm-up. What do we need to operate? How much time do we need to operate with the best quality of service? And which means we can also measure latencies differently. Like we can measure the latencies taking into account the entire lifetime of the application. Or we can start measuring and comparing latencies only when the application is warmed up. And this warm-up curve also depends on the, like, what do we use? Like if we use client VM, we'll have worse performance, but we'll have faster, much faster warm-up. But it's still different. It's still not instant. With native images and Crack, it's like much better. For native images, we'll have almost the same peak performance from the very beginning. Like, okay, we can start containerizing our deployment and take just one container. Put that application into a container. We don't need even Kubernetes here. And get the sanitizing result, the same number of requests per second, which is great. Some early experiments, that wasn't true. Like you put the application into container, or especially on in a single node cluster, and the performance changes. So that single node cluster, again, just one container, but also surrounded by all that ingress or proxying or load balancers or whatever. Just you have a single node, but you have all the resources. Or it can be like small one. Unfortunately, in that series of experiments, it's the same number. Surprise. Kubernetes doesn't cost us nothing. Well, it's good. Now we can try to chop this big node into smaller pods, having the same amount of resources. Actually, the larger amount of resources, because we tried to outperform the point where applications stopped scaling vertically. Like we've made some settings and we don't know what to do next, and we need horizontal scaling. So we need to use more resources, but we don't know how to properly set them up, right? So our horizontal scaling would be the most cost efficient, the best in terms of utilization. Okay, let's try this one. Hooray! We've got a larger number. So like 3 times better, right? 20K RPS from the entire system. But we still can use smaller pods, right? So let's chop the same node, and will the number be different or not? Yes, it will. It's worse. So we still have all that resources from the operations perspective. It's the same Kubernetes cluster. And even, well, the other story is that in one of large banks, our kind of customers, they say, we are not allowed to use, well, we need a special permission to use larger pod sizes. We only allowed like to take for free, to take without any permission, to take the smallest ones. It's okay. So they still consume the same total amount of resources, but they spend it inefficiently. Like, what's the point? Just people who decide that, they don't understand how it works. So yeah, let's go beyond that. Like half a CPU instance. What's the number of RPS? I don't know. I wasn't able to wait for it to start. Because it starts taking so much time to warm up, to actually bring your application up, just to get the service to respond to your first request. It's impossible. We've broken our application just by misconfiguring and providing the most cheap pods. Stupid. All right. So we know the best configuration, and we've determined it by performance testing. That's why we need it. It just gives us better results with the same hardware resources. So we pay same or less, and we get better cost model. We have better performance. So we earn more money, we get our bonuses. No. Happiness. Yeah. So native images also scale in the same fashion, right? We have to determine, but in this example, the number is different. But again, we have to measure, to compare, like what actually happens. So that's our strategy search pattern. We have to measure all that to try our experimental laboratory results in wild, using all that nice Kubernetes techniques, like A/B deployments, right? And we finally roll it out using some canary deployment and whatever. We follow CPU and RAM requests and limits, looking at the desired QoS for each individual service. Otherwise, well, another story is like a different bank. They called us and said, hey, we have crashes from time to time. Our applications are just killed by the host. Our pods are killed and we don't know what happens. So, well, what settings do you use? Like, such settings. Hey, it kind of looks strange. You have your XMX set higher than your limits for your pods. What's wrong? They work. Yeah, of course they work until they break. So that's a great example. They actually made the settings, but they've made the wrong settings. They haven't validated it, and they had, there must be some tool for it. I don't know, Kubernetes operator saying, hey, just don't deploy JVMs like that. Yes, let's build container images properly, get best results, and I'm not sure. If you have some time for a small demo, like maybe 10 minutes, okay. I'll just skip the fascinating conclusions and let's see what we can do with build packs. Just my favorite demo part. Because I think you get all the idea of that testing. So we'll look at the same application and we can mirror the screen. All right. Can you see it? Almost, right? Okay. Resolution. We can make the worst resolution. Oh. No. Yes. Okay. So my favorite ID is the text editor, right? So this is the example of the same pet clinic application, but the most, or almost, there is most recent. Anyway, probably the newest version. And I've made an optional setting here in the configuration of this plugin, overriding the build pack. So the default build packs give you the runtime stack, the base container you run on, with some Debian-based Linux layer. And as I mentioned, we provide our own Linux, which is kind of Alpine-like, and it's very slim. You've seen it already with Docker file-based images. And the default build packs for Spring Boot put Liberica JDK, but the standard JDK on top of that, on top of that Debian-based distro. And we also have specially crafted for the cloud. We have that Liberica JDK Lite distribution, which is somehow better if you create containers. So we can see that in action. And it's packed in a build pack. So the build stack here is referred just like a Docker image, a regular one, just one setting in your POM.xml file. And you still don't write Docker files by hand. So you still can build a container. Yeah, this is a log from your build. Let's try to find it. Where does it start? Yes, that's the run of container. Here, if we run the build, you'll see. Can you see anything? Mm-hmm. Great. That Maven performs lots of actions, but the majority of ones are related to pulling some special images, to build stuff, to compile your Java code, right? To create a native image if we use profile native. And after that, we create a layered resulting image, which has all that starter script. It has exploded fat jars, so it used thin jars, so it's easily updated. You only update tiny thin jar if you changed your application code. And it shows you all the settings used in the build process, like the number of Tomcat threads, for example, that directly influences the amount of native memory that you need, because every platform thread requires like 1 megabyte of memory. So you have to reserve that native memory, and a lot of other memory can be used for the Java heap. So, etc., etc. And finally, it says, hey, I've published the image into that your local Docker registry. So we can try to run it. And I actually have multiple images here. Let's look at them. So I have 5, but 2 ones are the same, in fact. So I'll make it more visible. So the lowest one is called JVM default. It takes 350 megabytes on disk. It's much better than the manual written Docker file from OpenJDK. And it also performs all that nice actions. So we'll see it in action, but it takes 350 megabytes. And if I build default as a native image, I'll have 248 megabytes on disk. But it will transfer that much of data every time we update it. Because not that much, but what it was, 150 megabytes every time. The base layer will still be the same. We can create the native with Beltsov base image. That will be smaller, like 216 megabytes, but still large updates. And we can create the smallest one with the classical JVM and Alpakita Linux as the baseline. It will be less than 200, like 191. So let's start some of them and look how it works. For example, we can start with the JVM default build pack. So the idea here, we only change a setting in POM.XML, and we can get really different images, really different performance characteristics, just looking at what we need. Just do it, just experiment and compare it. Saying, hey, Docker, please run this container for me. And you see it's a classical JVM startup. So it takes like 7 seconds or so, 6 seconds to start, right? So definitely a classical JVM. And we can check that this image is up and running, right? It's here. We have mapped the port. And we can just easily check the amount of memory usage and CPU usage. And let's restart it just to look what happens when we start the image. See the CPU usage here. It is really raised just when we start the application. No load is put on it. It's just being started. And then it's finally up to 0. But we consume like 340 megabytes in memory. Okay, let's start a different variant. Let's say here's the native one, the native default. We start it, well, 65, yeah, JVM default. Let's start the native default. Bam. It's there. You know the peak performance is worse, but the startup is instant. You just get it up and running, like 0.6 seconds. And if you need to be started up even faster, you can use Crack. What? The classical JVM is better than native image. Yes, it can be. Because with native image, we still perform some initialization, but we don't perform any compilations. With restoring from the checkpoint, we get all that. We get some compiled methods, but not all of them. But we don't perform initialization. We have all that initializers pre-run, so entirely. And we can check the Docker stats. Like 200 megabytes, 264, right? So it's much better. So we had 340. Oops. Let's start it again. It's easy. 100. Maybe it will take some more. Great. It's running. So let's get back to the classical JVM, but the one which is based on Alpaca and Linux.
That's the native. That's the native one.
Is it? Oh, yes. Okay, thank you. Yeah, just I couldn't trick you that easily. All right. We would notice it when it starts, right? Yeah. And by the way, you see all that options detection, right? So you see, it detected the actual limits of the container. It subtracted all the reserved data, all the required memory for all native things as we know it and set by certain settings in the POM XML. That's crazy. We just tune a few settings in that XML file. That's it, and we get the container. So it also provides us statistics about the classes, right? All that helps us to tune it if it fails. It could be easily fixed. So it has started, and we can again sorry. Yeah, so it's 338, and it was originally 339. Typically, it's like 360 in the original run and like 330 in Alpaca run. Couldn't trick you again, but it's still lower. And you see, you get all the final statistics, all the initial things, all that build packs magic. It's still there for you. And we can as well build the native image with Alpaca build packs. And finally, this is it. Let's run it. 0.4. It shouldn't start faster. In fact, it should be the same. It depends on the frequency, because currently it's a dynamic frequency in this laptop, and it depends. But we finally get below 100 megabytes consumed by this running container. So we reduced our memory consumption like 3.5 times, 3.7 probably. Just by using one string in our build command and one setting in the POM XML. And we still don't write it that fast. And all the memory settings are calculated for us. Cool. But we must measure other performance characteristics of that resulting containers to compare them. Because what's important for us? What are the trade-offs? What's the balance? Well, just try it, check it, and, well, save on your cloud costs. Thank you. Do we have any questions? Yes.
Yes. On your example where you split until you reach the 0.5 CPU, I know there is a JVM flag to tell the JVM that there is more CPUs, or at least virtual CPUs, than the one it auto-detects.
Yes.
Could that help in case where you have, for example, applications like Office applications which can have different loads depending on the moment of the day, but not all of them at the same time. And if you put requests which are too high to reach that minimum amount that you need to have for the peak, you are in the end underusing your.
I see. Yeah, you probably mean active processors count, which is the major setting here. Yeah, of course, there is like act as a server machine and use container support and other flags. but that's probably the one.
Mm.
Like, likely it won't help.
Okay.
I should say this setting it higher than the amount of CPU resource, like turned into number of CPUs available to your container, in fact, seems to be harmless. So if you say have like 4 CPUs, if you turn your quota to your to a number of CPUs, and you say I have 40 active processors, that surprisingly will be rather harmless. It will become harmful if you have a lot of GC, like that.
Okay.
Like the number of GC threads will increase, and they will just steal all the CPU from your actual business code. Having that much lower than the actual number of CPUs is really harmful. So definitely harmful, you will just underutilize things. But it's not that bad still, because it doesn't influence all the threads and thread pools that you derive manually. So that basically has an impact on the system thread pool, on your GC threads and JIT threads, JIT compiler threads. But JIT is smart enough just to keep it low, then the number of threads low if you don't need them. GC may require a lot of.
Because for the fortune point, for example, since its size is decided at start,
Yeah. So
it's based on the request and not the limits.
At some point it was a thing in build packs, it was a bug, like it was calculated and set not entirely correctly, but now it's just don't touch it. Unless you really need to set it and you know it. So if you need to respond to load, so you either say, okay, we have certain degradation, or we just reach the limit and we have a cap, or you scale. So don't try to trick it. You don't get the resources out of nowhere. Yeah. Right? Yes.
Question, but I don't know if I'm a complete newbie when it comes to this, but from what I understand then, because in our project we just have a simple Docker file, and honestly I have not touched it. It was there from when I started working there, and
Right.
it runs, and that's it for me. But from what I can understand, it seems like this build pack system would be more or less like a free win, basically, instead of writing the Docker file by hand.
In most cases, if you start from scratch, or just you have some Docker file and want just, can it be better if someone maybe does something better for me? Definitely, yes, try it. There are different build packs, by the way. Just Paketo is one set, Heroku does it soon, and we've made our own one. And there are limitations. So we saw things that are harder to make with build packs. Sometimes they start limiting you. But as a starter, and as an example, like just sketch how you should build your manual deployment. It's just great. Just follow the same practices and succeed.
It's the same with Spring Boot, because a lot of configuration,
Yes.
the convention that they
Yes,
put is
stay with the default.
About a lot of stuff that a lot of people already spend a lot of time thinking
Exactly.
about, so you don't have to. And most of the time, it's what you probably need, right?
Yes. Yeah, thank you. Interesting questions. Just let's throw in some more. No?
Okay. Thank you again.